in my last lecture, near the end of that lecture, we had started the angular momentum problem in quantum mechanics, and we will continue our discussion on that and discuss the eigenvalues and corresponding eigenfunctions for the angular momentum. We had said that we represented, as in classical mechanics, by the r cross p, but now p is a differential operator. So, for example, Lz will be equal to y p x minus x p y. So, the cross product is x cap, y cap and z cap, and x, y, z, p x, p y, p z. So, the p x, p y, so I am sorry. So, this will be Lz will be x p y minus y p x, and similarly Lx, similarly Ly. So, this, if I write the differential operator representation, so this becomes minus I h cross x delta. So, Lz operating on a wave function psi will be delta psi by delta y minus y delta psi by delta x. Now, I want to express this in terms of the spherical polar coordinates r theta phi, so that we know what is x, that is r sin theta cos phi. So, the first term, so x delta psi by delta y will be equal to r sin theta cos phi multiplied by. Now, I want to express this in terms of spherical polar coordinates. So, it will be delta psi by delta r times delta r by delta y plus delta psi by delta theta into delta theta by delta y plus delta psi by delta phi into delta phi by delta y. This is the first term, and the second term will be y delta psi by delta x, and this will be r sin theta sin phi, and delta psi by delta x will be delta psi by delta r. Y here will be replaced by x, delta r by delta x plus delta psi by delta theta by delta x plus delta psi by delta phi, although it looks very cumbersome, but the analysis is quite straightforward. So, as you can see, we require therefore delta r by delta y, delta theta by delta y, delta theta by delta x, delta phi by delta y, delta phi by delta x, and delta r by delta x. So, these are the expressions that we would like to express in terms of the spherical polar coordinates. So, as we had said that the spherical polar coordinates were defined as r sin theta cos phi was equal to x, r sin theta sin phi was equal to y, and r cos theta was equal to z. So, if you square and add, then it will become sin square theta cos square phi, sin square theta sin square phi. So, if you add them, it becomes sin square theta plus cos square theta. So, r square is equal to x square plus y square plus z square. Okay. So, if I differentiate with respect to x, so it becomes 2r delta r by delta x is equal to 2x. Therefore, we will have delta r by delta x will be equal to x by r, but x is equal to r sin theta cos phi. So, this will be sin theta cos phi. Similarly, 2r delta r by delta y. Now, when I write this partial differentiation, when I differentiate partially with respect to y, then x and z have to be kept constant. So, this will be equal to 2y. So, this will imply that delta r by delta y is equal to y by r, that is sin theta sin phi. So, you can see these are not that difficult. Then let me write the expression for tangent of phi. So, I divide this equation by this equation. So, I get tangent of phi becomes equal to y by x. Y by x. So, this equation, if I differentiate this, so you will get secant square phi delta phi by delta x will be equal to, if I differentiate this with respect to x, so this will be minus y by x square. So, this will be minus y is r sin theta sin phi divided by x square, that is r square sin square theta cos square phi. So, as you can see, if I multiply secant square phi to cos square phi, it will become 1. So, I obtain delta phi by delta x is equal to minus 1 over r sin phi over sin theta, because sin theta and sin square theta, 1 sin theta cancels out. So, this is one result. If I differentiate with respect to y, that is very simple, secant square phi delta phi by delta y will be just 1 over x, and 1 over x is r sin theta cos phi. So, if I multiply this, 1 cos phi will cancel out with secant phi, and then cos phi will come on the top. So, I will have 1 over r cos phi over sin theta. This is one expression. And the last expression is that if I square these two, so x square plus y square is r square sin square theta, x square plus y square is r square sin square theta, and z square is r square cos square theta. So, r square cancel out. So, you are left with tan square theta, sorry, this is tan square theta is equal to x square plus y square divided by z square. So, if I differentiate this with respect to x or y, let us differentiate this with respect to x first. 2 tangent theta secant square theta delta theta by delta x is equal to 2x by z square. So, this implies that this is the right hand side is equal to 2 r sin theta cos phi divided by r square cos square theta. So, r square cos square theta, this cos square theta and secant square theta cancel out and 2 cancels out. So, therefore, this implies that delta theta by delta x will be 1 over r, the 2 also cancel out, sin theta cos phi by tan theta. Tan theta is sin theta over cos theta. So, this will be just cos theta cos phi. Finally, if I differentiate with respect to y, then again 2 tangent of theta secant square theta delta theta by delta y, this is equal to 2y by z square, that is 2 r sin theta sin phi divided by r square cos square theta. Once again, this term will cancel out with this term, and therefore, this will be delta theta by delta y will be equal to 1 over r cos theta sin phi. So, we have now expressions for delta r by delta y, delta r by delta x, delta theta by delta y, delta theta by delta x, delta phi by delta y and delta phi. So, I just have to substitute it here. Before we proceed further, let me warn you a little bit about the partial differentiation. That you see, let us suppose I want to calculate delta r by delta x, then y and z are to be remain constant. So, therefore, I must express r in terms of x, y, z. And now I differentiate with respect to x, delta r by delta x becomes 2x, and this gives delta r by delta x is equal to x by r. Now, let us suppose I wanted to differentiate delta x by delta r. Then I must express x, because when I differentiate with respect to r, theta and phi remains constant. So, I must express x is equal to r sin theta cos phi, and if I differentiate this delta x by delta r, and here theta and phi remains constant. So, this becomes sin theta cos phi, and this is also x by r. So, you can see that delta r by delta x happens to be equal to delta x by delta r. Now, in total differential, you know that dy by dx is equal to 1 over dx by dy. But in partial differentiation, one has to be very careful as to when you are differentiating partially with respect to x, then y and z have to remain constant, and when you are partially differentiating with respect to r, then theta and phi are to remain constant. So, these are some of the tricks. So, therefore, our objective was to obtain the operator representation of Lz. In the Cartesian coordinates, it is x delta psi by delta y minus y delta psi by delta x. But I wanted in terms of the polar coordinates And so, therefore, you have to evaluate this, which we have evaluated. All these are evaluated. So, for example, delta r by delta y is given here, delta r by delta x is given here, delta theta by delta y, delta phi by delta y is given here, delta phi by delta x is given here. So, everything is there. So, we just have to substitute those expressions in this, carry out a simple manipulation, and one finally obtains this remarkable result, that Lz psi becomes equal to minus IH cross delta psi by delta phi. It simplifies to this particular relation. Now, let me try to find the eigenvalues of Lz. So, what is an eigenvalue equation? If you recall that for the Hamiltonian, the eigenvalue equation is H psi is equal to E psi. That is, this is the operator operating on a wave function. E is a number multiplied by the same wave function. Then this equation is known as the eigenvalue equation. So, I would like to find out, say, Lz psi, the eigenvalues and eigenfunctions of the operator Lz. So, let me write it down as, let me try to solve this eigenvalue equation, lambda h cross. I introduced h cross just for the sake of simplicity, delta psi. So, lambda z psi, Lz psi is equal to minus h cross is just a constant, delta psi by delta phi. The eigenvalue of the operator Lz I have represented by lambda h cross. The eigenvalues of the Hamiltonian that we have been solving till now are the energy given by E. So, this is equal to lambda h cross psi, h cross cancel out. If I multiply both sides by I, then I get delta psi by delta phi is equal to I lambda psi. This is a very simple integration, that psi becomes the phi dependence. One cannot say anything about the theta or r dependence. The phi dependence becomes e to the power of I lambda phi. Now, any wave function has to be well behaved, has to be single valued. That is, on the xy plane, please see, on the xy plane, this is the angle phi. If I go around the origin and I make phi to phi plus 2 pi, I arrive at the same point, and the wave function must have the same value. So, therefore, e to the power of I lambda phi plus 2 pi must be equal to e to the power of I lambda phi. Therefore, we obtain the result that e to the power of I 2 pi lambda should be equal to plus 1, and therefore, from this we immediately obtain that lambda has to be equal to a positive or negative integer. Lambda must be positive or negative integer, where m can take the values 0, plus minus 1, plus minus 2 only. So, the eigenvalues of the operator Lz are given by Lz psi is equal to m h cross psi, where m is equal to 0, plus minus 1, plus minus 2 and so on. And what are the corresponding wave functions? Therefore, the solution of the eigenvalue equation, Lz psi is equal to m h cross psi, where m will take the values 0, plus minus 1, plus minus 2, etc. And the corresponding phi dependence, only, one cannot say anything about the r and the theta dependence, will be e to the power of I m phi, and to normalize it you will have under root of 2 pi. These wave functions are usually denoted as capital phi subscript m as phi. And because of this normalization constant, if you have phi m square d phi from 0 to 2 pi, phi goes from 0 to 2 pi, this will be 1. This is known as the normalization condition. And the second is that if you have 0, this can be also proved that very easily, phi m star prime phi multiplied by phi m phi d phi, this will be 0 for m not equal to m prime. This is known as the orthogonality condition. So, therefore, we have been able to find that the operator Lz, we have been able to solve this equation. Lz has the eigenvalues m h cross, multiples of h cross, where m can take, and we have used the condition that the wave functions have to be single valued, that as I go from the point phi to phi plus 2 pi, the wave function must remain unchanged. Using this single valued condition, that the fact that the wave function should be single valued, we obtain that lambda should be either a positive or a negative integer or a 0. So, these are so what are the eigenvalues of the operator Lz? The eigenvalues are m h cross, where m is equal to 0, plus minus 1, plus minus 2, etc. Now, we have obtained the operator representation of the operator Lz. Very similarly, you can obtain for Lx and Ly. So, Lx, as you know, will be Lx operating on psi will be minus I h cross y p z, that is y delta psi by delta z, minus z p y, that is delta psi by delta y. And again you express this in terms of spherical polar coordinates, and if you do that algebra, then we obtain a slightly cumbersome, just it is not cumbersome, just a little detailed algebra, and one has to keep track of the factors. I h cross sin phi delta by delta theta plus cot theta cos phi delta by delta phi, and Ly is equal to I h cross minus cos phi delta by delta theta plus cot theta sin phi delta by delta phi. And of course, we had obtained that Lz is equal to minus I h cross delta by delta phi. Now, I want an operator representation of L square, and L square is defined as Lx square plus Ly square plus Lz square. Lz square is very easy to obtain. Let me do this. Lz square psi, the square of an operator is just Lz operating on Lz times psi. So, if you do that, so this will be minus h cross square delta 2 psi by delta phi square, del by del phi and then again del by del phi. But for others it is not that simple, but fairly straightforward. So, Lx square will be Lx square psi, I will just write down the expression, and that will be equal to minus h cross square, and then you will have sin phi delta by delta theta plus cot theta cos phi delta by delta phi. This is Lx times Lx, that is sin phi delta psi by delta theta plus cot theta cos phi delta by delta psi by delta phi. Then I have to operate this on this, operate this on this, operate this on this, operate this, and we have to be very careful. When we differentiate with respect to theta, then of course phi can be kept constant. So, if I operate this on this, the first term will be very simple, sin square phi delta 2 psi by delta theta square. But when I operate this on this, there is a term here depending on theta. So, one has to be a little careful. Similarly, I can it is advisable that you do this once, and it will allow you to get used to the way in which one deals with these operator algebra. Similarly, one can calculate Ly square, and we had already Lz square psi, which was the easiest to calculate, which was h cross square delta 2 psi by delta phi square. If you add these up, then surprisingly this L square of psi, which is Lx square plus Ly square plus Lz square, this comes out to be minus h cross square 1 over sin theta delta theta sin theta delta psi by delta theta plus 1 over sin square theta delta 2 psi by delta phi square. So, this is the expression that comes out for the operator L square. Now, our object is to find we have found out the eigenvalues and eigenfunctions of the operator Lz, and that was very simple. We had found out that the eigenvalues were mh cross, and the eigenfunctions were 1 over root 2 pi e to the power of I m phi. Our next step, which is not that easy, is to find out the eigenvalues and eigenfunctions of the operator L square. So, I write this down as equal to lambda h cross square psi, and I want to solve this. So, our objective now is to solve this particular equation. I have introduced h cross square for the sake of convenience. So, the h cross square which are constants get cancelled, and I bring this term to the left hand side. So, I obtain 1 by sin theta delta by delta theta sin theta delta psi by delta theta plus 1 over sin square theta delta 2 psi by delta theta square plus lambda psi, which is now a function of theta and phi, is equal to 0. I want to solve this equation. Our objective is to find the values of lambda and the corresponding wave functions. That is a very important problem. Now, we use the same method, namely the method of separation of variables. So, psi of theta and phi we write down as f theta multiplied by capital phi of phi. I am sorry, this is phi square. So, I substitute this. So, I get, if I substitute it here, so let me do it step by step. Phi of phi divided by sin theta, and now I can write a total differential d by d theta sin theta df by d theta plus 1 over sin square theta. So, f will come outside now, f of theta sin square theta d2 phi by d phi square plus lambda f into phi. Have the variable separated out? Not yet, because this involves phi and theta, this involves phi and theta, this involves phi and theta. But what we do is that we multiply the whole equation by sin square theta divided by f times phi. So, please see, if I multiply the whole equation, then I get 1 over f, because phi, this phi will cancel out with this, 1 over f sin square theta by sin theta, that is sin theta d by d theta sin theta df by d theta. What I will do is, I will write this term first and take this term to the right hand side. So, I write plus lambda sin square theta is equal to minus 1 over capital phi d2 phi by d phi square. Capital F is assumed to be a function of theta. So, now as you can see, the variables have indeed separated out. The left hand side is a function of theta, the right hand side is a function of phi only. So, a function of theta cannot be equal to a function of phi unless both of them are equal to a constant. So, I put this equal to m square, a square of the number, and the reason is that I will come out in a moment. So, let me solve this part first. So, this part will come out if I just look at the phi part. So, I will obtain 1 over phi d2 phi by d phi square plus, if I bring it here, then it is minus minus plus m square is equal to 0. This will imply d2 phi by d phi square plus m square capital phi of phi is equal to 0. The solution of this is extremely simple. We have phi of phi is equal to again e to the power of I m phi, and as we had just discussed a few minutes back, if for the wave function to be for phi of phi to be single valued, m must be equal to 0 plus minus 1 plus minus 2 etc. That is, if you increase phi to phi plus 2 pi, it must give me the same wave function, that is e to the power of I m phi must be equal to e to the power of I m phi plus 2 pi. As I increase phi by 2 pi, I must get the same value of the function, otherwise the wave function will be multiple valued. So, you will have e to the power of I 2 pi m must be equal to 1, and therefore, m must be equal to 0 plus minus 1 plus minus 2 etc. So, we have found one part of the solution, and to normalize it, these form a orthonormal set of complete set of orthonormal wave functions. So, these are which we had obtained. These are also eigenfunctions of the LZ operator, the eigenfunctions of the LZ operator, m is equal to 0 plus minus 1 plus minus 2 etc. So, we come back to this equation and we find that m square must be the square of an integer. Can I put this equal to a negative constant? The answer is of course we can, but if you solve this, then the solutions will be of the form of e to the power of m phi, which are not single valued function. And so, therefore, this has to be put equal to a positive constant. If I put equal to a negative minus m square, then the solutions will be exponentials, and those will not be single valued. So, therefore, we have solved the phi part of the equation rigorously. Now, let me solve the theta part of the equation. So, we have here, so let me write the theta part of the equation, and it will be something like this. So, minus m square, so sin theta divided by f of theta d by d theta sin theta df by d theta plus lambda sin square theta minus m square is equal to 0. I multiply the above equation by f of theta divided by sin square theta, and I will get 1 over sin theta d d theta of sin theta df by d theta plus lambda minus m square by sin square theta f of theta equal to 0. This is known as the associated Legionnaires equation. The solution of this equation is little complicated, but of course, people have found the solutions. What we will do is find the solution for m equal to 0. For m equal to 0, the above equation becomes 1 over sin theta d d theta of sin theta df by d theta plus lambda f of theta equal to 0. Now, I introduce a new variable x, which is defined to be equal to cos theta. So, I write this in terms of this. So, df by d theta will be equal to df in terms of the x variable x dx by d theta, that is minus sin theta. So, if I multiply by sin theta, so then this becomes sin square theta, and that is equal to minus df by d theta 1 dx 1 minus x square. And then you can calculate what is d by d theta. I have just done that, and final result will be that d of dx of 1 minus x square df by dx plus lambda times f of x is equal to 0. This is very simple. This is known as the Legionnaires equation, which you must have studied, but in any case we will obtain the solution of this particular equation. We rewrite the Legionnaires equation. We differentiate the first term to obtain 1 minus x square d2f by dx square, and the differentiation is minus 2x df by dx plus lambda f of x is equal to 0. This is also another form of the Legionnaires equation. Here, as we know that x is equal to cos theta, and so therefore, x lies between plus 1 and minus 1. Now, we solve this Legionnaires equation by the power series method. By the power series method, which is also known as the Frobenius method, and we assume a solution of the form f of x is a sum a r x to the power of r plus s, and the summation is over r goes from 0, 1, 2 to infinity. This power series method, which we had encountered while solving the confluent hypergeometric equation, is one of the very powerful methods for solving a second order differential equation. This is also known as the Frobenius method. Now, I substitute this solution in this differential equation. So, I will get 1 minus x square, and if I differentiate this equation twice, this expression twice, so I will get a r. First differentiation will give me r plus s, and the second differentiation will give me r plus s minus 1, x to the power of plus s r plus s minus 2, and the summation is over r equal to 0 to infinity minus 2x, and if I differentiate this once, so you will get a r into r plus s into x raised to the power of r plus s minus 1 plus lambda and summation a r x to the power of s plus r is equal to 0. As you can see, if I multiply x here, so this becomes r plus s, and if I multiply x square here, so this again becomes r plus s. So, essentially we have two terms. First, I multiply 1 by this, so I obtain this expression only. So, summation a r plus s into r plus s minus 1 x raised to the power of r plus s minus 2 minus, and if I take to the other side, alright, let me put the minus sign here, minus a r. Now, if I multiply x square here, as I just now mentioned, it becomes x raised to the power of r plus s. So, it becomes r plus s into r plus s minus 1, and I have taken the minus sign out. So, this is plus 2 into r plus s, and since I have taken the minus sign outside, so this is minus lambda into x raised to the power of s plus r is equal to 0. So, now this expression, if you take r plus s outside, so this becomes r plus s multiplied by r plus s minus 1 plus 2. So, this becomes r plus s plus 1 minus lambda. And so, since this minus this is 0, so I take to the other side of the equation. So, I will obtain summation, and let me multiply the equation, the entire equation, multiply entire equation by x to the power of 2 minus s. So, the left hand side becomes summation a r plus s r plus s minus 1 into x to the power of r, because I have multiplied by x raised to the power of 2 minus s. So, this term goes off. So, r is equal to 0, 1 to infinity, and on my right hand side becomes a r plus s, this term, plus r plus s minus 1 plus 1 minus lambda times x raised to the power of r plus 2, because I have multiplied by x raised to the power of 2 minus s. So, this becomes like. So, both the sums are from 0 to infinity. Now, this equation, as we had mentioned earlier, is valid for all values of x. So, I make an expansion. So, the first term is a 0 r equal to 0 s into s minus 1 x to the power of 0 plus a1 r s plus 1 into s multiplied by x, and then we will have plus summation a r plus 2. I replace r by r plus 2. So, then r goes from 0 to infinity. You see, I have taken out the first two terms outside. So, r plus 2, that means r plus s plus 2 and r plus s plus 1 x to the power of r plus 2. This is equal to the same what is written above, that is summation r equal to 0 to infinity a r plus s, the same term within brackets r plus s plus 1 minus lambda multiplied by x raised to the power of r plus 2. Now, each term, the coefficient, this is an equation which has to be valid for all values of x. So, that the coefficient of x to the power of 0 must be 0, coefficient of x to the power of 1 must be 0, coefficient of x to the power of 2 must be 0, and so on. So, the first term gives a 0 s into s minus 1 must be equal to 0. The second term will give a 1 s plus 1 into s is equal to 0, and the third term will give a r plus 2 multiplied by this will be equal to a r multiplied by this. So, I obtain a r plus 2 divided by a r will be equal to r plus s plus 1 minus lambda divided by r plus s plus 2 into r plus s plus 1. This is known as the recurrence relation, because using this equation I can determine a r plus 2 in terms of a r. Now, in this equation there are two roots, s is equal to 0 and s is equal to 1, and the root s is equal to 0 makes a1 indeterminate. So, there is a theorem in the theory of differential equations that if one of the roots makes a1 indeterminate, then that particular root, that is the root s is equal to 0, will determine both the solutions. So, this is the root of the indicial equation which will determine both solutions, and we will show this in a moment. So, we will just assume s is equal to 0, and if I assume s is equal to 0, then my recurrence relation becomes very simple. If I substitute s is equal to 0, then the recurrence relation becomes a r plus 2 a r is equal to r into r plus 1 minus lambda divided by r plus 2 multiplied by r plus 1. Since a0 will be related to a2 and a2 will be related to a4 and so on, we will have therefore, so this is the recurrence relation. This is the recurrence relation, and this is the root of the indicial equation. So, my solution will be, the solution f of x can be written as like this: two independent solution. The first term consists of only even powers a2 x square plus a4 x4 plus a6 x6 and only the even powers, plus a1 x plus a3 x cubed plus a5 x5 and so on. Because a2 is related to a0, a4 is related to a2. So, we have the odd even series and then we have the odd series. Now, we can see from this from the recurrence relation that as r tends to infinity, for large terms, this the dominating term here becomes r square, the dominating term in the denominator becomes r square. So, a r plus 2 divided by a r tends to 1. So, they are equal. So, if I choose a large enough value of r, let us suppose x to the power of 100, then beyond that all the coefficients are equal. That means, let us suppose after x to the power of 100, I can write this down, that is a 100 and then it will be 1 plus x square plus x4 plus x6. This is a divergent series at x is equal to plus minus 1, and therefore, it will blow up at x is equal to plus minus 1. It diverges at x equal to plus 1. And so, therefore, for the solution to be well behaved, we must terminate this series. We must turn this infinite series to a polynomial, and that will happen if lambda is equal to L into L plus 1. If lambda is equal to L plus 1, that is L is equal to 0, 1, 2, 3, then and then only will one of the infinite series become a polynomial. Let me illustrate this. Let us suppose I take L equal to 2. So, lambda is equal to 6, lambda is equal to 6, and so therefore, we will have from here, if lambda is equal to 6, so then we will have a r plus 2 divided by a r is equal to r into r plus 1 minus 6 divided by r plus 2 into r plus 1, and let me take the just the even series. So, a 2 by a 0, that is r is 0. So, this becomes minus 6, r is 0 to 2. So, this is equal to minus 3, and a 4 by a 0 will be equal to r is 2. So, 2 into 3 is 6 minus 6. So, this is 0. So, therefore, the even series will become a polynomial, and we will have a 0. So, f of x, the even series will become a 2 plus a 2 x square plus a 4 x 4. So, a 0 is a 0, let us suppose, and a 2 by a 0 is 1 minus 3 x square plus a 4 is 0. So, this is the polynomial solution, and the polynomial solution is known as the Legendre polynomials, PL of x, and we assume that PL at x is equal to 1 is 1. If I do that, then this becomes the P2 of x, this becomes 3 x square minus 1 divided by 2, where we have chosen the value of a 0 such that at x is equal to 1, P2 of 1 is 1. So, we will continue from this point onwards in my next lecture.